So we're going to have potential energy initial plus work equals what kind of energy exists at the end? Why do you think there is kinetic energy at the end? Yes, but it's bounced now to a maximum height of 2.4 meters. At that maximum height, it's not going up anymore. So it's just potential. So this is going to be mgh initial plus some work is going to equal mgh final. So my work is going to be mgh final minus mgh initial, which is going to be 0.25 times 9.8 times 2.4 is the final height it rises to, minus 0.25 times 9.8 times 3.2. That height is, sorry, that work value is then going to be what? Answer my question.
Well, look at this. You have to go through this.
I will let you know when it's important that you know. Brendan, what's the value you got? Okay. Shouldn't be very big.
I got negative 1.96.
Perfect. That is what you're looking for. And in the answer key that I didn't give you, the answer is right there. See? Right there. 1.96 joules. In the key I didn't give you. Sorry? It should be negative, because you have lost energy. But the question does say what is its loss in potential energy, so you could quote that as, you could say the loss is 1.96 joules, or you could say negative 1.96 joules, depending on just, the verbiage. They mean the same thing. That was question 8. Relatively straightforward, yes? Okay. Then, let's just do the last example here, and we'll talk a little bit about springs. I'm not going to do a spring example. Maybe I will do a spring example. We'll do a spring example, but I want to do the last one of these, and then I want to give you a bunch of time to play with this stuff, just to make sure we're all on the same page here. Question number 5, or example number 5 here was the last one that we maybe could have gone through yesterday, but didn't have time for. Several students are pretending that they are in the jungle while playing in Ravine Park. Do students still go to Ravine Park? Is that a thing? Manuel goes to Ravine Park? Okay. They suspend a rope from an overhead tree limb. A student of mass 70 kilograms running at 8.0 meters per second grabs the rope and swings off of the ground. What maximum height does the student reach? So here's what you've got. I once drew this amazingly in the past. Let's see if I can draw it amazingly again. So you've got a tree. For some reason, this is how I drew it before, so this is how I'm going to draw it again. Trees like this don't have branches like I'm about to draw them, but let's assume you've got a board. We nail this board to a tree, and we're going to suspend a rope. There's the rope. And here is Jeff. He's giving her. Sorry? You understand the drawing?
No, I totally understand it.
Okay.
I'm just saying that board, like that, on the tree.
Yeah. Oh, the structural engineering is terrible. So Jeff's giving her, he's going to grab the rope, and all of his kinetic energy at this stage is going to get converted into potential energy as he rises up into the air, eventually looking like this. There's a rope. Okay, how did I draw this before? I was pretty proud of this one before. There he is. I practiced. Question we're being asked, what is that height? All of this is work energy. So all of it is going to start from that point. Energy initial plus work equals energy final. So what kind of energy does he have at the beginning? What kind of energy does he have at the end? And is there any work done that is mentioned in the question? There's kinetic energy at the beginning. As far as this problem, the way it's worded and all that stuff is concerned, is there any work being done? If work was being done, what would the form? What form would that take? Friction, yeah.
No, I would say friction.
You got a haircut.
Since Monday, but you see short in the front.
Oh, okay. So you didn't get a haircut?
Yeah, I didn't like it, but
So you did get a haircut.
yeah, I did, yeah.
Okay,
Yeah,
it looks
since Monday, but
since Monday, and it's Thursday, and I'm now just noticing.
yeah.
Looks good. Sorry, I don't like it. Does friction show up at all in the formulation of the question? No. So, and friction is the only thing that's going to take energy out. And there's no mention of anything putting energy in. It's not like he grabs the rope and then as he's swinging up, he like turns on a rocket booster to propel him further forward. Or no one grabbed his butt beneath him and pushed him up higher, right? No one has added energy to the system. So no, there is no work being done as far as how this question is outlined. Now, when he reaches his maximum height, what kind of energy does he have? Potential energy. Is that the only thing he has?
Kinetic final.
Does he have kinetic energy at his maximum height? At maximum height, it's defined to be the maximum height because you're not moving. You are no longer going up. And you have not yet started to fall down. So there is no kinetic energy at this point. All we want to know is at the absolute maximum, as he starts to swing back down, it'll be like, it will start to go negative again, but we're not there. It's just at the top. So this is all we've got. We've got a kinetic energy initial and equals a potential energy final. So we're going to have 1/2 mv initial squared equals 1/2, nope, I lied, equals mgh final. So we can put some values in here. This person weighs 70 kilograms, but we have no work term here. So we can cancel out the masses, which is really interesting. So we're going to have 1/2 8, which is our initial velocity squared, is going to equal 9.8 hf. So what's that final height going to be? Bless you. .27 meters. Can someone confirm Zaid's result? Cool. The interesting thing here is the masses cancel. How fast would a 60 kilogram student have to run to reach the same height as the 70 kilogram student? What did you say, Luis?
The same because that cancel, so doesn't matter.
You bet. Love it. So let's look at one more style of question. I don't have a lot of these, but I do have a few. Unfortunately, I have to take up one of them. I think I've got 5 that I'm giving you. Flip the page. Find me this page here. I have not yet given you any examples of what it would look like to include potential energy for a spring. So I figure I've given you some questions here. I just want to do one of these with you just to make sure that we're feeling okay about all of this. And then I will release you. Spend the rest of the class working on just figuring this stuff out. Number 5 is the one I want to do together. We're going to do this as an example. A 10-gram pebble is placed in a slingshot with a spring constant of 200 newtons per meter and is stretched back 0.5 meters. What is the maximum velocity the pebble will acquire? That's cool. So let's draw a slingshot. But it's a side view of a slingshot, so, all it looks like is a stick. Maybe we can give it some depth. Turn it on its side a little bit. Where'd pink go? Here's pink. So we got that guy attached there. We got that guy attached there. And we've got a pebble. What is going on here? There we go. It all starts, like dynamics, all started with F net equals ma. This all starts with work energy theorem. What kind of energy does our pebble have to start? What kind of potential energy? There's going to be potential energy, yes, but it's going to be spring potential energy. If we wanted to, could we talk about gravitational potential energy? If we wanted to, we could, because, this obviously isn't at ground level, but where is the pebble going to be traveling the fastest if I shoot this thing horizontally? But where is it going to be the fastest it's ever going to be? As soon as it leaves the elastic, yes. So as soon as this elastic slams back into the slingshot and our marble is flying through the air having just left the slingshot, that is where it's going to be traveling its maximum possible speed. What is interesting about the marble at that location and the marble at that location?
The marble in the first location has no kinetic energy. The marble, when it's been shot, has the most kinetic energy.
So you're telling me there is a kinetic energy final. That's true. That doesn't tell me anything about location, though. Like when I say location, I literally mean physical space within the universe that it's occupying. Talk to me about those two locations. Sorry? That's true. What else do we know? Yep, that's what Tenjot said. Yeah, that's true. Yeah. Give you a hint. I'm trying to make a statement about potential energy, gravitational potential energy here.
Calculate the force, we do vertical and horizontal.
No. But that. Because this object and this object, if you're shooting a slingshot over level ground and you're shooting at level, in a perfect world, the height of the marble or the pebble when it's pulled back and the height of the pebble or marble as it leaves the elastic are going to be the same. So at that, I can call that height my zero height, right? So because of that, we're able to ignore potential gravitational energy. Do you see the point I'm trying to make here? We're cool with what I've said?
Because we don't, like, we just want the velocity, like the maximum speed, so we don't care about the when it's going to fall or anything else.
Sure. If I shot this thing downwards, though, all of a sudden I would have to, or upwards even, all of a sudden I would have to start taking into account gravitational potential energy. But typically we shoot a slingshot sideways. This is how it's being shot. So this is what we've got. And as far as the question is concerned, is there any work being done between here and here? No. As the pebble flies, yeah, it's going to experience air resistance. But in this, it's not going to. So this is all we've got. We've got our potential energy spring is being turned into kinetic energy of the stone, or the pebble. So the potential energy for a spring is given to us by what formula? Say it, Connor.
Half kx squared.
You betcha. So a half kx squared is going to equal a half mv squared. So this is going to be 1/2. We know it's 200 newtons per meter. We know the extension is half a meter. And that's going to equal 1/2. We know the mass is 10 grams. So what is 10 grams in kilograms? Zero 0.01, good. V squared. So how fast is our object going to be moving? The halves can cancel, so we don't need to include them in our calculation. Make it a little bit easier. Good question. Is it 100? I didn't get 100. Yeah, I got 70.7 or 71 meters per second.
I agree.
Which is 254 kilometers per hour. Just to put that in perspective.
What?
That's 254 kilometers per hour. That slingshot is, or that stone is just trucking.
Would that be like the actual, like an actual slingshot right there, or like is that just like
That's good. I don't know. I don't know what the spring constant of the band in a slingshot's going to be. I've seen people shoot through plywood with a slingshot, so I'm willing to bet these are reasonable values. I saw someone,
plywood with a
they put a marble through a piece of plywood with a slingshot, yeah.
like
like 1/4 inch plywood. You can do a lot of damage with a slingshot. That's why it's been a useful hunting tool forever. So that's it. So this is how, I mean, ultimately, fundamentally, nothing has changed here. We're just now bringing in an additional form of potential energy. And this is what you're going to need when we go and talk about this bungee. Because, well, the opposite thing is actually going to happen here. When you throw your little egg off of the platform, what kind of energy is it going to have to start? It's going to have what kind of potential energy? Gravitational potential. And as the object falls, it's going to be gathering kinetic energy. But then at the bottom, it's going to start to stretch this thing, like a bungee jumper would, gaining what kind of energy?
Potential sling.
Elastic potential energy. So what you've got from the beginning to the end is you've got gravitational that's turning completely into spring, because you gained a bunch of kinetic energy and then all that kinetic energy was lost again at the bottom. Ideally, you want no kinetic energy at the bottom, because if you have kinetic energy at the bottom, what's going to happen to your egg? It's going to plow into the ground. So what we're going to do is we're actually going to, our expression for this activity is going to be a little different. You're going to have gravitational potential energy here and spring potential energy over here. But in this one, you see that kind of thing like that. So I think there's about a half hour left in class, maybe 35 minutes. What I want you to do is I want you to do the rest of these work energy problems. As you get the handle on these things, they'll go quicker. Just like that one and the page before. The rest. Except for that number 10. I want you to do 9, 11, 12, 13, 14, and then the spring ones 1 to 4. And I'll come around and I'll help you as is necessary. Question 13 is a gooder. 13 brings back the incline stuff I gave you last chapter. I like 13.
Not a good thing, sir.
1, 2, 3, 4, 6, 7. Yes, I do. I'll put them on the screen. I don't have the spring ones, the 4 spring ones. I'd have to do them to get you a key. But these are the values that should give me the rest of up to 14. Be careful with how the questions are worded. It will apply to certain things. Happy to help you with this as you deal with this. James, he's here today. Clearly. Right. Yes, no, James is not available. You may. No, I need to do that.